there and welcome to another tutorial for the Edexcel Further Pure 1 math syllabus. This is another video on matrices and linear transformations with matrices. In the previous video I just introduced the fact that a matrix can represent a linear transformation. In this particular video we are going to make sure we understand the geometrical transformations of various matrices, and we're going to identify and use matrix representation in order to do the following transformations: reflecting the coordinate axes, rotate by multiples of 45 degrees about 0, 0, and enlarge about the center 0, 0 with a given scale factor. We'll do combined transformations in a future video. Okay, to start with, I would like you to have a go at thinking about how you could work out what the following matrix transformations actually do. Have you got any idea on earth what you might do to work out what these matrices do? Well, what you could do, an idea that you could do, is you could think to yourself, what would happen if I apply that matrix to the unit square? If I applied it to the corners of the unit square and then drew in what happened afterwards, I would have myself an idea of what that matrix then does. Okay, so there's the unit square, and I'm going to say this here is O, and its position vector 0, 0. This here I'm going to call it A, and I'm going to say it's 1, 0. This here I'm going to call B, and I'm going to call it 1, 1. And this here I'm going to call C, and it's going to be called 0, 1. If I applied that matrix to this square and see where it ended up, that might help me decide what that matrix actually does, or what transformation is represented by that matrix. Okay, so I'm just going to shrink this, and I'm going to pop this over here for future reference. You should be able to apply a matrix to the corners of that square. What you would do is you would take this matrix 3, 0, 0, 3, and you would multiply it by 1, 0. Sorry, you would multiply it by 0, 0, the first, this one here, 1, 0, this one here, 1, 1, this one here, and 0, 1, this one here. Okay, so let's multiply that out. This times this would give me 0 up here, and this row times this column would give me 0. This row times this column would give me 3. This row times this column would give me 0. This row times this column would give me 3. This row times this column would give me 3. And this row times this column would give me 0. And this row times this column would give me 3. So when I apply this matrix, okay, so this is my transformation. When I apply it to the unit square, so these are the corners of the unit square, that's my input, this is my image. Okay, so these would be the points. 0, 0 stays where it is, 1, 0 goes to 3, 0, 1, 1 goes to 3, 3, and 0, 1 goes to 0, 3. And if I draw that in, what has happened to this shape here? It is a square, but it has been enlarged by a scale factor of 3. So this matrix represents an enlargement by scale factor equal to 3. Okay, so the general idea, if you want to find out what a matrix does, what the transformation matrix does, apply it to the unit square, see what happens to the unit square, and then decide what transformation that actually is. It should be quite easy to decide. Now I'll leave B and C for you to try yourself. So on the next slide you're going to try B, and after that you're going to try C. And just to help you, I'll delete these, and on the next slides I'm going to put in the unit square for you to start with. So I'm going to keep this for you. And I'm going to paste it on the next slide. So I'm just going to take that, sorry, Control C. There you go. So you try and do B yourself and work out what the effect of that matrix transformation is. Pause the video, have a go. Well, if you took this matrix, -1, 0, 0, -1, and you multiplied it by 0, 0, 1, 0, 1, 1, and 0, 1, hopefully with a bit of luck you realise you got yourself 0, 0, you got yourself -1, 0, you got yourself -1, -1, and you got yourself 0, -1. Okay, what does this image look like? Where is this image? Well, 0, 0 stays where it is. This one here goes to -1, 0, so it goes over here. So I'm going to call that A dashed. This one here is -1, -1. I'm going to call that B dashed. And this one here is 0, -1. I'm going to call that C dashed. This clearly, if I draw this in here, this is a square as well. But how have I got from the first square to that square there? What has happened? Well, I'm fairly sure you can see that what has happened. Is it a reflection? There's no sort of reflection that gets us there. What's happened is that you have rotated this square 180 degrees anti-clockwise in order to move this square to that square. So it's a rotation. This represents a rotation. And with matrices and transformations, we always tend to go anti-clockwise. So stick with that convention of 180 degrees anti-clockwise. And what's the center of rotation? Well, it's about 0, 0. And so we have, by seeing what happens to the unit square, found out what this matrix here does. That matrix rotates 180 degrees anti-clockwise about the origin. Okay, so we'll have a go at another one. C, pause the video, have a go yourself. Okay, so if we were to take the matrix 0, -1, -1, and 0, and we were to multiply it by the corners of the unit square, so 0, 0, 1, 0, 1, 1, and 0, 1, what would we get? Well, we would get 0, -1, sorry, we would get 0, 0 in the first column, 0, -1, -1, -1, -1, 0. So let's draw this out. O stays where it is, it's at 0, 0. A now it was at 1, 0, now it goes to 0, -1, so it goes down here. I'm going to call this A dashed. B goes to -1, -1, so I'm going to call this B dashed. And C goes to -1, 0, C dash is going to be over here. If I draw in what this looks like, this clearly again is a square with sides 1. However, what transformation gets you from the green square to the blue square? Well, if you think for a little, hopefully you'll realise that it's a reflection in the line y is equal to -x. So it's a reflection in that line there. So this matrix here represents a reflection in the line y is equal to -x. And so you have found what each of those three transformations are, what each of those three matrix transformations are, by seeing what happens when you apply them to the unit square, and then it's obvious to you what they are. Okay, next I'd like to show you a shortcut that might annoy you. Instead of multiplying like a matrix by the unit square, we can take a shortcut. And this is why the shortcut works. So take a general matrix A, B, C and D. That's any general linear transformation matrix. And see what happens when you apply that transformation to the position vector 1, 0. What do you get? We'll multiply that matrix out. I'll let you do that. But you should get AC. So, and if you do the exact same thing, A, B, C, D, A, B, C, D, and you multiply it by the point 0, 1, the position vector 0, 1, what do you get? Well, you get B and you get D. Okay, so what? What does that tell you? Well, just draw a picture first of all before I fully go into it. Here's the plane, and 1, 0 can be represented by that vector 1, 0, and 0, 1 can be represented by that vector 0, 1. They are two of the corners of the unit square. Now, what this is telling me up here is when I apply any matrix in the world, any linear matrix in the world to 1, 0, I get back this. How does that relate to the initial matrix? Well, look, AC, AC. If I apply a matrix to 1, 0, I always get the first column of that matrix back. If I apply a matrix to 0, 1, I always get the second column of that matrix back. So, for example, in our previous work, we were asked what does this matrix do, something like this. What does that do? Well, straight away, I knew if I applied that to the vector 1, 0, I get the first column back. So I know that if I know for sure, I don't even have to work it out. I know that if I apply that to 1, 0, I get the first column back, I get 2, 0. And I know if I apply this to 0, 1, I get the second column back. Okay? So I know, where did 1, 0 go? Well, it went to 2, 0. Where did 0, 1 go? Well, it went to 0, 2. And I could draw those in like that. That should be a straight line. That should be a straight line there. What transformation is that? Well, clearly, it's an enlargement by scale factor 2. About the origin, about 0, 0. So all I had to do was, when I looked at the matrix, the first column told me where the 1, 0, or this, sometimes we call this the I vector, where that ended up. And the second column always tells me where 0, 1, or what I sometimes call the J vector ended up. And I could draw it straight away on my picture, and I could know the transformation straight away. So what I'm going to do, I'm going to give you an opportunity to go back to the ones we've just done and double check you can do it this quicker way. Pause the video, take a minute or so, try and work through these and draw out the pictures, and I'll go through in 1 minute just to show you how much quicker this way actually is. Okay, so here's my picture. Actually, what I'll do instead, I'll draw out a picture, and this will apply for each of them. So I'll draw out a picture there. Okay, let's do part A. Where did 1, 0 end up? Well, 1, 0 ends up where the first column, of the matrix ends up. So it ends up at 3, 0. And where does, I should make that have the same colour there. And where does 0, 1 end up? Well, 0, 1 ends up at the second column, 0, 3. you can clearly see what is this transformation. Well, it's an enlargement by scale factor 3. This one's gone over here, so it's been enlarged by 3. This one's gone up by a factor of 3. It's an enlargement by scale factor 3. Done. It's as simple as that. Let's do the next one. Where does this end up? Well, it ends up where the first column of this matrix is. So negative 1, 0, negative 1, 0. It ends up over here. And where does this one end up? Well, it ends up at the second column, which is 0, negative 1. There. If I called that, let's say, A, that would be A dashed. If I called that B, that would be B dashed. Okay, how do I get from one to the other? Well, again, clearly it's a rotation of 180 degrees anti-clockwise. About 0, 0. And it's quicker that way than drawing out what happens with the unit square. Okay, so what next? Take those away there. Again, I should call that A, and I should call that B. The last one, what happened to 1, 0? Well, it went to the first column of this matrix, 0, negative 1, and 0, negative 1 is down here, and that would be A dash. And what happened to 0, 1? Well, it went to the second column of this matrix, negative 1, 0, which is over here. What transformation is going on there? Well, I think it's pretty obvious, and we've done this before, but it must be a reflection in the line y equals negative x, y equals negative x, a reflection in that line. Now, hopefully you can see this shortcut is very helpful, because rather than multiplying out each of the corners of the unit square, all you've got to do, in order to be able to solve this, is draw out your 1, 0 and 0, 1, your I and your j components. Your I component, after the transformation, will always go to the first column, and your j component, after the transformation, will always go to the second column. And so, you know exactly where those 1, 0 and 0, 1 ended up. Draw yourself a picture, and the transformation is very easy to find. Okay, we're going to use that idea in order to actually find matrices if we are told the transformation. So remember this idea said that if we take a transformation A, B, C, D, and we apply it to 1, 0, I get the first column back. And if I take the same matrix A, B, C, D, and I apply it to 0, 1, I get the second column back, BD. Okay, so how could we use this? Well, if we're told the transformation, if I'm told, say, a rotation, let's say 90 degrees anti-clockwise, about 0, 0, and I'm asked what matrix, how on earth could I do that? Well, all I would have to do, very simply, is I'd have to draw out a little picture to help myself. I'd have to draw out 1, 0. I'd have to draw out 0, 1. Okay? And all I'd have to do is then decide where they go after a rotation of 90 degrees clockwise. Well, clearly, where would 1, 0 go after that? 1, 0 would go to the point 0, 1. Okay, if I rotate that 90 degrees anti-clockwise. And this one here, 0, 1, well, where would that go? Well, that would go to the point negative 1 and 0. So, when you apply your transformation to that point, you get this. When you apply your transformation to that point, you get that. And we know applying your transformation to this vector gives you the first column. And when you apply a transformation to this vector, you always get the second column. So I know the first and second column of the matrix, and the matrix, therefore, would be 0, 1, negative 1, 0. As simple as that. I could tell you what the matrix is for a rotation 90 degrees anti-clockwise about 0, 0 by just seeing what happens to the I and j components, this I component here and this j component here, drawing it, seeing where they ended up, and where they ended up, where the I component ended up, will be the first column of the matrix that represents it. So that will be the first column of the matrix. And where the j component ended up is the second column of the matrix. And therefore you have your matrix. Okay, we are going to try and do this for some quite difficult examples coming up. What I'd like you to do is maybe have a go yourself at each of these, pause the video, but then work through my solutions to see if you got them right. Here's the first one. Find the matrix transformation to represent the following. A rotation of 45 degrees anti-clockwise about the origin. Have a go yourself, see if you can get this. Okay, this is more complicated. The algebra is a little bit messier, but the idea is exactly the same. Draw a picture. This here. 1, 0. This here is 0, 1. If you rotated those 45 degrees anti-clockwise, where would you end up? I might call this point A, and I might call this point here B. Where would you end up? Well, let's move A. If I moved it 45 degrees, A would end up something like this, where that's 45. I'm going to call that A dash. Where would B end up? Well, B would end up somewhere over here, 45 degrees. That's 45, so that must be 45 as well. 45 degrees, and that would be B dash. This here would be a right angle between them. Okay, where is A dash and where is B dash now? Well, i.e., when you applied this transformation that you're looking for to 1, 0, what did you get back? When you applied this transformation to 0, 1, what did you get back? Well, I can easily find A dash. Look, I know that this here has length 1. I know that has length 1. Okay, because this had length 1 here and I've just rotated it up. So that's got length 1. And I know that angle is 45. So if I want to find out how far across it now is, how far across this is, okay, what I'm looking for, I'm trying to find the adjacent. I've got the hypotenuse, so I use cos. Okay, remember I would use cat. And if I want to therefore find the adjacent side would be equal to cos 45 times 1. And cos 45, if you type that in your calculator, is root 2 over 2. So this distance is root 2 over 2. So where did this end up? How far across did it end up? Well, it ended up at root 2 over 2 across. How far up did it end up? Well, that means I want to find this side here, which is the opposite. So I use SO. If I want to find the opposite, it's going to be sine 45 times the hypotenuse, which is 1. And if you type in sine 45 in your calculator, you again get root 2 over 2. So 1, 0 goes to root 2 over 2, root 2 over 2. That there is going to be the first column of our matrix. Now, where does this one end up? We'll do trigonometry similar. How far back is it? What's the x-coordinate back? It's the exact same triangle as this one, apart from your back here. This is clearly going to be negative root 2 over 2. And how far up? Well, it's the same as this one. It's very clear. Do trigonometry using that as 1 and that 45, but clearly you can see it is root 2 over 2 up. So therefore, where does this one end up? Well, it ends up at negative root 2 over 2 left, and it ends up at root 2 over 2 up. So this therefore must be my first column of the matrix. So the matrix therefore must be equal to root 2 over 2, root 2 over 2. and this is the second column, so negative root 2 over 2 and root 2 over 2. And that matrix there is the matrix that gets us that rotation 45 degrees about 0, 0. That's about as hard as it gets with multiples of 45 like that. Okay, I'd like you to try another one yourself, example 3. Try the same process, draw the picture out, see what happens to the I and j vectors, and then that would give you the first and second columns of the matrix. Have a go at this, pause the video, I'll go through in 10 seconds. Okay, so a reflection in the y-axis, what I'm going to do is draw a picture. So, draw yourself a picture. Draw out your I and your j. Draw out 1, 0. I'm going to call that point A. I'm going to draw out 0, 1. I'm going to call that B. And I'm going to reflect it in the y-axis. So reflection in the y-axis, let's draw the y-axis out. The y-axis is clearly this one here. So I'm going to reflect those in that axis. Now where does A end up? Well, A, when reflected, I'll call it A dashed, will end up here, which would be at minus 1, 0. Where would B end up? Well, B dash would end up at the exact same point. It wouldn't go anywhere. So this transformation, this reflection, when I apply it to 1, 0, I get negative 1, 0, and that's going to be my first column. And when I apply this matrix to 0, 1, well, I get 0, 1 back. So that's going to be my second column. And so I've got my matrix. This matrix is therefore negative 1, 0, and 0, 1. And that there is the matrix that represents a reflection in the y-axis. Okay, last one for you to do yourself. Pause, have a go, then I'll go through in a second. Okay, how would I find the matrix to represent this? Well, again, draw yourself your picture. Draw yourself out your I component, if you will. Call it A, maybe 1, 0. Draw out your J component, which I might call B is 0, 1. And enlarge these with a scale factor of center 0, 0, scale factor negative 2. Where would A end up? Well, if I multiply all this by negative 2, it would end up at negative 2, 0. So it would end up over here. So A dash would end up at negative 2, 0. Where would B dash end up? Well, times that by negative 2, the whole thing, it would end up at 0, negative 2. That would be my B dash. Okay, so this transformation, when I applied it to 1, 0, I got negative 2, 0. When I applied it to 0, 1, I got 0, negative 2. This here must be the first column. This here must be the second column of that matrix. So therefore the matrix must be negative 2, 0 and 0, negative 2. And that represents a enlargement center 0, 0, scale factor negative 2. And that's all I wanted to say on finding matrices for transformations. So to consolidate your work, I'd suggest read chapter 4, page 86 to 90, look at the examples, and then do every question on exercise 4E, page 90. That would be great practice for you. Thank you for watching.